Hello, this is Jeff Hamrick again at the University of San Francisco's Financial Analysis program. I'm going to talk for a few minutes about using ordinary least squares regression to extract the deterministic component of a time series. So the example I'm going to focus on will be the same as the one that we considered in class. I'm going to import this set of data related to beer sales in Australia. It's a comma delimited text file, and we need to add a time index to this data set. I happen to know that that these beer sales began in January of 1956 and they go on to August of 1985. So I'm going to reflect that fact when I set up the time variable. I'm going to create a time variable called time. It's going to be a monthly time index. It'll start with 1956 month 1, and we'll add n-1 to it to create that monthly time index. I'll go on ahead and declare this data set to be a time series data set. Time will be the time index, and it's a monthly variable, which I'll let Stata know with this particular option right here. And if I browse, I can take a look at the data set right here and see that we've got 1956 month 1 and so on and so forth, and as soon as we hit month 12 it cycles over again to month 1. Okay, so let's go on ahead and take a quick look at this this time series plot of these data. Beer is going to be the time series of interest. Because I've declared it to be a time series, it's going to read off the time index for the x-axis. So here's the beer data, and what we can see from this picture are a couple of features. That there's a linear trend upwards that kind of levels off. There's also clearly a seasonal effect here that we might want to account for if our goal is to account for the deterministic component of this time series. So what I'm going to do is use ordinary least squares regression along with the definitions of some new variables to kind of identify one possible candidate deterministic component of this time series. So let's begin by simply regressing against time itself, that is linearly. So if I regress beer against time, what I see is that I get a pretty good accounting for most of the variability in the y variable, that is to say beer. But this is not going to be a very good accounting, because we know that there's more than a linear component to this time, to the trend. So let's account for more by creating some new time-based variables and adding those to the regression model. So let me next, let's see, add a variable that's going to account for the sort of quadratic effects of time. So I'll create a variable called time equals, quad equals time squared. That's going to be a quadratic order term that will account for sort of the quadratic effects of time. And if I now regress against beer, time, and this quadratic variable, we get an even further improvement, in fact. So that's pretty good. So there might be another way to account for that kind of leveling off in the time series, which is to add a log linear time trend. Let's try creating a variable called log time, and that's just going to be the logarithm of time. At least that's going to be my first attempt here. And notice that we have a little bit of a problem here. 49 missing values were deleted when we created the logarithm of time. And the reason for that is because you'll recall that Stata indexes the first moment in time to be January the 1st, 1960, when we use a monthly time index. And that means those values before 1960 got assigned negative integer indices in the Stata time storage system. And that means that we can't take the logarithm of them, so they end up missing. So to fix that, what I'm going to do is let me remove, we can do it this way, or we can come up here and I can drop this variable. Let me kill that variable log time and recreate it by doing gen log time. And I'm simply going to translate the Stata stored values of time forward by, let's say, 50 increments to create a new logarithmic variable. This is a bit arbitrary. We could put 100 plus time. That is the logarithm of 100 plus time. But the point is to account for kind of the overall logarithmic shape of the curve. So it shouldn't matter too much what we do. So let me create this variable and then update my regression model so that I regress beer against time, the quadratic order effects, and the logarithm of time. And as you can see, I once again get somewhat of an improvement, But I think ultimately what we're going to need is we're going to need to account for that seasonality. And so as we discussed in class the other day, two good functions from basic calculus or basic high school algebra to account for that seasonality, at least using deterministic ordinary least squares regression, would be the sine and cosine function. So let me create another variable called gen, and it's going to be called sine time, and I'm going to do the sine of, well, what I'd like to do is the sine of time. The problem is that the sine function has period 2 pi, as you guys might remember, and we want this to have period 12, since we have monthly data that we expect to have a natural season of 12 months. So the way we fix that is to multiply by 2 times pi, and then to divide by the new period, the period we know that the data have naturally. Okay? So if I do this to define a variable called sine time, and I do this to define a variable called cosine of time, let's update the regression model one more time. So let's regress beer against time, the quadratic term of time, logarithm of time, sine of time, and cosine of time. Okay, so first of all, notice that given these particular definitions for the variables, all of them are highly statistically significant. I'm not sure that we have a great case to throw any of them out. We explain, even though this is kind of a strange thing that we're doing since we're regressing against purely deterministic functions of time, we explain a large percentage of the variation in the beer data using this particular regression model. This might be the extraction of the deterministic component of the time series that we want to use after all. So let's get a visualization of this. So if I create, using predict, the predicted values of beer under this time series, if I do predict y hat or predict y hat comma xb, that's going to create predicted values of beer under this regression model that we've created. So here it's added that variable right here, and now I can use tsLine to visualize both the real data, the beer data, and y hat, the predicted data, underneath this regression model that we last created. And so what we can see here is that by no means is the model perfect. We have some problems in the sense that we seem to do really well at the beginning, and then we seem to be missing some of these very particular peaks right here towards the second half of the time series. There might be a couple of other things that we could do to modify this regression model to better account for that. I'm going to suggest that the problem is that the seasonality here is what we call multiplicative rather than additive, and a good way to handle that is with the Holt-Winters smoothing process, which I'll talk about in a separate Stata video. So for right now, this is going to be the way that I'm going to extract a new time series to model around this deterministic trend that we've created. That is, I'm going to take the beer data and subtract off the y hat data, and that would be those set of residuals for this OLS model would be the residuals that I would try to overlay an ARIMA or SARIMA style model on to improve my predictions above and beyond what we get with this pure OLS model that we've created in this demonstration. Okay, so this is how we use Stata to create an OLS deterministic time trend for a time series model. Let me know if you have any questions